You ever feel like your computer's trying to juggle, I don't know, 5 things at once and none of them seem to be going fast?
Oh, absolutely. It makes
Mhm.
you wonder how they actually um, manage all that, right?
Exactly.
Yeah.
So today we're going to dive into, well, 2 really key ideas behind how efficient apps get built: concurrency and parallelism.
Yeah, and these terms, they get mixed up all the time. People kind of use them interchangeably.
But they're not. And understanding the difference, it really sheds light on how software handles, the workload.
Totally. And it's not just like theory. Knowing this stuff helps whether you're, coding something, prepping for a tech discussion, or even just curious about why your apps work the way they do.
Right. So our mission today, let's nail down that difference. Define them, sure, but also talk about how they work, what they're good at.
And how they actually relate to each other, because they are connected.
Okay, let's jump in. Concurrency. That's usually the first one people think of, right? Handling multiple things.
Yeah, think of it like a really good chef, one stovetop, but maybe 4 pans cooking different things.
Okay.
They can't stir all 4 at the exact same instant, but they can switch really fast, right? Stir the sauce, flip the veggies, check the meat, back to the sauce.
So it looks like everything's cooking at the same time, even though it's just one chef moving quickly.
Exactly. That's concurrency on, say, a single CPU core.
Hmm.
It's rapidly switching between tasks, user input, file reads, whatever,
Giving each one a little slice of time.
a tiny slice. It creates the illusion of doing things simultaneously.
And that quick switch, you called it context switching.
Yep, context switching. The CPU has to save where it was in task A,
Its current state.
right, its state, what data it was using, then load the state for task B and work on that for a bit, then maybe switch back around to task C.
Like pausing one video game and jumping to another, but remembering your save point.
Perfect analogy.
Yeah.
But there's a catch.
Oh,
All that saving and loading,
eh,
it takes time. It's overhead.
it's not free.
Definitely not. If you switch too much, too often, you can actually spend more time switching between tasks than actually doing the work in the tasks.
So it's a balancing act. Concurrency is about managing tasks, making sure everything gets some attention.
Precisely. It's about progress across the board, not necessarily finishing things at the exact same microsecond. It's smart management.
Okay, so where does this juggling act really pay off? What's it best for?
It's fantastic for tasks that involve waiting. We call them IO-bound tasks. Input, output.
Like waiting for data from a slow hard drive or the network.
Exactly. While one task is just sitting there waiting for that data to arrive, a concurrent system doesn't just idle.
The CPU can switch to another task that's actually ready to compute something.
You got it. It makes the whole system way more efficient. Think of a web server, maybe on one core.
Right.
It's handling requests. While one request waits for the database, the server can work on sending a page back to another user or processing a new incoming request.
So it feels responsive to everyone, even though it's technically only doing one tiny thing at any given millisecond.
That's the magic of concurrency. But what if you don't just want responsiveness while waiting? What if you need raw speed for, heavy calculations?
Okay, yeah, what then?
That's where parallelism comes in. Think more cooks, more stovetops.
Okay. So if concurrency is one chef juggling pans.
Parallelism is like having, say, 2 or 3 chefs in the kitchen. Each has their own burner, their own cutting board.
Okay.
One chef's just chopping veggies. Another is just searing the meat. They're working completely independently, but at the exact same time.
On different parts of the same overall meal, maybe.
Could be. Or totally different tasks. The point is, multiple things are happening simultaneously. True simultaneous execution.
And in computer terms, that means using multiple CPU cores.
Bingo. Multiple cores, each working on a separate task or a separate piece of a larger task at the exact same time.
No illusion here, it's actual parallel work.
Right. Each core cranks away on its assignment independently.
And that leads to faster results, I assume?
For the right kind of work, absolutely. Big speed gains.
Yeah.
Especially for tasks you can easily break down into independent chunks.
So parallelism is less about managing waiting and more about throwing more processing power at a problem.
Yeah, that's a good way to put it. It excels at computationally intensive stuff.
Like what? Give me some examples.
Okay, think big data analysis, crunching huge data sets.
Right.
Or rendering complex 3D graphics for, movies or games.
Oh yeah, rendering takes ages.
It can. But if you can render different frames, or even different parts of the same frame, on different cores simultaneously.
Speeds things up dramatically.
Exactly. Same for scientific simulations, modeling weather, or how molecules interact. Super complex calculations.
You split the problem up and run pieces in parallel.
You got it. That's how supercomputers tackle those massive problems.
Okay, so we've got concurrency for responsiveness, especially with I/O,
Mm-hmm.
and parallelism for speeding up heavy computation using multiple cores.
Mm.
So where do we see these in action? Like everyday tech?
Oh, they're everywhere. Really working together often. Web apps, like we mentioned,
Right, concurrency keeps them responsive.
definitely. Handling all those user clicks, database lookups, background jobs smoothly.
But what about parallelism in web apps?
Well, maybe the server itself has multiple cores to handle more concurrent users truly in parallel, or maybe a specific background task like processing an uploaded image gets broken down and done faster using parallel processing.
I see. And machine learning, training those huge AI models.
Oh, parallelism is critical there. You're processing massive amounts of data,
They're
with
right.
tons of math,
Trying to do that on one core would take forever.
literally forever for some models. So you distribute the data, distribute the calculations across many cores, sometimes even across clusters of machines.
Makes sense. And you mentioned video rendering before.
Yeah, processing multiple frames at once across different cores. Big time saver.
What about big data tools like Hadoop or Spark?
Textbook parallelism. They're designed to chop up huge data sets and process the chunks in parallel across a whole cluster of computers. That's their whole reason for being.
Okay, so it's clear they're both super important. Now, you said they're related. How do concurrency and parallelism actually, connect?
Well, think about it. Concurrency, in a way, can enable parallelism.
How so?
Because when you design your program using good concurrent principles,
Yeah.
you're already breaking it down into smaller, potentially independent tasks or units of work.
Right, like the different functions handling requests or database access or UI updates.
Exactly. You've structured it into these manageable pieces. Once you have that structure,
It's easier to then say, okay, if I have multiple cores available, let's run this piece on core 1 and that piece on core 2 at the same time.
precisely. Concurrency gives you the logical separation of tasks, the structure.
Yeah.
Parallelism is then about taking advantage of that structure on hardware that supports running multiple things truly simultaneously.
So concurrency is kind of like the blueprint, the organization.
Yeah, I like that. It's the architecture.
And parallelism is like building it with multiple construction crews working at once, following that blueprint.
That's a great analogy. And many modern programming tools have features that help you write concurrent code and make it easier to automatically leverage parallelism if the hardware is there.
So designing for concurrency first often makes achieving parallelism easier down the line.
Often, yes. It helps you think about how to decompose the problem effectively. But there's a flip side, too.
Oh.
Sometimes just throwing more cores, more parallelism at a poorly structured program doesn't help. If the tasks aren't really independent, or if the overhead of managing all those parallel threads is too high,
It could actually slow things down.
it absolutely can. You need that good concurrent design, that smart structure, to really benefit from the extra hardware.
Fascinating. So it's not just about hardware, the software design is crucial. Okay, this really clarifies things. Now, speaking of robust systems, we should mention our sponsor, StoneFly.
Right. So StoneFly, they've been innovating in data management for a good while now. They offer, well, a really broad set of solutions: SN, NAS, S3 compatible object storage,
The whole storage spectrum, basically.
pretty much. Plus backup and DR, cloud stuff, and even getting into advanced AI and security tech. From a technical angle, they've got some serious features.
Like what stands out?
Things like immutable snapshots, which are key for reliable recovery. You can't accidentally change them. AES 256 encryption, both for data sitting there and when it's moving.
Essential for security.
Totally. Then there's synchronous and asynchronous replication for keeping data safe across sites, smart tiering to manage costs, flash caching for speed, and really important these days, ransomware volume protection.
Yeah, ransomware is a huge concern.
Definitely. And StoneFly has this patented, immutable, and air-gapped repository tech. Air-gapping is a big deal for ransomware protection, plus things like compass mirroring. And it's all manageable through a single interface, even if you have tons of nodes across different locations.
Sounds comprehensive. So who is this aimed at?
Well, really, anyone looking at options for, say, data protection, scaling storage performance, or maybe doing an infrastructure refresh could be for primary storage, backup, DR, hyper-converged setups, servers, virtual environments, VMware, Hyper-V, Proxmox. They cover a lot.
And they position themselves as affordable.
Yeah, they aim for enterprise features, but accessible pricing, backed by good support. And they have this promo of the month thing.
Okay.
Right now, there are two options. One is a really low-cost way to try their immutable air-gapped backup, like $10. Or, for bigger needs, there's a 70 terabyte backup and DR appliance.
70 terabytes, that's pretty beefy.
It is, and it scales way up to 4 petabytes. It includes those air-gapped and mutable features, works with Veeam, Rubrik, Commvault, etc., and even has an AI appliance with object lockdown tech for ransomware defense. That whole package is $700 right now.
Wow, okay. And how do people find out more?
Best bet is to email their team, sales@stonefly.com. That's sales@stonefly.com. They can walk you through the details and see if StoneFly solutions fit your needs. StoneFly really offers a solid suite for managing and protecting data.
Good to know. Thanks for that overview of StoneFly. All right, let's wrap up our concurrency versus parallelism discussion. Quick recap.
Sure. Core difference. Concurrency is about managing many tasks, often to keep things responsive, especially when waiting is involved. I/O. Think juggling.
Right. Illusion of simultaneity on potentially limited resources.
Exactly. Parallelism is about doing many tasks simultaneously using multiple resources, like CPU cores, to get computationally heavy work done faster. Think multiple workers.
True simultaneity for speed.
Yep. And crucially, they're related. Good concurrent design, breaking tasks down well.
Often makes it easier to actually execute those tasks in parallel if you have the hardware.
You got it. Concurrency can be the foundation that enables effective parallelism. They often work together in modern systems.
Okay, makes total sense. Concurrency manages, parallelism accelerates. Different goals, but linked. So, here's a final thought to leave folks with. Processors keep getting more cores, right? And software keeps getting more complex. How do you think this whole interplay between concurrency and parallelism is going to change? How will it shape software design and, performance in the future?
That's the big question, isn't it? Definitely something interesting to watch.